you got to know all of E&M come May, not just what we're working on today. So first of all, we have this B dot dl, I believe, equals mu naught IC. Yes? That C does not stand for trapped in does not mean going through the loop. That IC actually is conductive current, which we'll talk about later on when we get to Maxwell's equations. Because there's actually something that's not a conductive current, and you might say, what the hell is it? We'll talk about that later on. Now, because of this dot product, Ampere's law is only useful when there is high degree of symmetry. Meaning, if not parallel or perpendicular, don't use it. Flat out, that's your rule for Ampere's law. If it's not easy, where you can say that the dot product, they're either crossed or they're parallel, you just don't use Ampere's law. Is it still valid? Yes. It's just not easy for you to do it. Could they probably work it out with some sort of dot cross product and all that crap? Could a professor do that? I'm sure there are ways of dealing with that, not in this class. Okay? Now, you need to choose your Amperian path to make it easy. So, the one that we've been doing is we have a wire that we are looking at from N, yes? And so what do we do? And we say that there's current flowing throughout that wire. Now, in other words, there's current coming throughout this wire towards us, okay? Is everybody following what I'm doing there, yes or no? Would you accept this? Okay. If I had a single strand of wire coming out, think about this like that, the wire that I showed you where it's got all these little strands of wire, right? Well, if you've got a strand of wire coming out of the page toward you, doesn't the magnetic field go this direction, counterclockwise?
Yes.
Each of them is little counterclockwise. Now, if I had, here's the logic that I've got to prove to you also. So we get that the magnetic field is going to be going this direction. Yes? That's going to be the magnetic field at any point in the wire as you go out. At any radius of R, the magnetic field is going to go this direction. Yes? I'm looking around the room and you know if people are following me on that, yes or no?
Yes.
Yes? Okay. If I did this, if I had two wires, at this point right here, they would cancel, wouldn't they?
Yes.
We all agree with that?
Yes.
Okay. What if I did this? What if I took a bunch of wires and I did this? If I were to take a point out here, okay, these are wires. If I take this point out here, and I take this one right here, I would see that its magnetic field goes this direction. This one, the magnetic field goes the same way. This one, the magnetic field would go kind of this direction. This one, the magnetic field would kind of go that direction. But there would be a net magnetic field going down. As if you combine all of these into one big wire and it would do that. Everybody in agreement with that?
Yep.
But what if I took a spot right here? If I take this spot inside the wire, and this would be the net. If I take this spot, well, this one right here, from the top one, would be going like this. This bottom one would go the opposite direction, but it would be weaker, wouldn't it? You see, it would be weaker because it's farther away. But do we see how many of them are close up here, and how many of them are down here? Even though these are farther away, there's more of them. And without taking the time, next chapter in APC, I'm going to prove to you to this inside of a sphere. Using, it's not exactly right, but it's close enough to prove it to you. But can we get the logic that at this point right here, even though these over here, this one and this one, that one's down and this one's up, so they kind of cancel each other. But these are all going that direction, and these all have a net going the opposite direction, but they're farther away, but there's more of them. You follow what I'm doing or not? Therefore, inside of current, inside of a wire, the outside layers of the wire do not matter. Only the inside parts of the wire matter. So as I'm trying to find the magnetic field at a radius of r, I only care about the strands of the wire inside of r. I don't care about the ones that are outside of r. And that's why Ampere's law is the enclosed current. Okay? You have to find how much current is enclosed in the Amperian space. Yes or no? So, if I had enclosed half the wire, if I have a quarter of the wire, I have a quarter of the current. So I need to know how much of the current I have at a radius of r. This all sounds slightly familiar, doesn't it? So if I take this distance and I were to call it r, then I need the amount of I in the circle of r. Well, what is that? It's a percentage. So if you had 100% of the wire, you'd have 100% of the current. So the current enclosed will equal the area enclosed divided by the total area times the total current. I need to pause to make sure that people understand the logic. We don't need the whole current, the whole wire. Why? The outside, anything outside of our radius gets canceled. Only what's inside of our radius matters. Are we all in agreement with that?
Yes.
Can we all find the area inside of little r? What would that be? A enclosed would equal pi little r squared. A total would equal pi, and we're going to call that big R for the total radius. Yes or no?
Yes.
So my I enclosed will equal pi little r squared over pi big R squared times the current in the wire. And the pi's cancel. No more pi, very sad. Okay, so now we have our enclosed current. Yes or no? You can write this down again. It's all, we've done this before, but if it helps you to write it down, that's fine. What you better do is go home and figure this out, because I'm thinking next week we need to do something where this is a, we need to make this an all or nothing, not an all or nothing, what it's called, an essential quiz, right? Where you just flat out got to get it right. So here we go. The magnetic field and dl. What does that mean? Well, if this is r, this are all our little dl's. And aren't our magnetic fields parallel to dl in all places? The magnetic field is going like this. So we choose a path. We choose a path parallel to B at all places. We understand what I just said? We choose it to be parallel to dl at all places. Therefore, the dot product does what?
Goes away.
It completely disappears. And since in all of those places, is B varying or is B a constant? B is a constant, so it can come out of the integral. And all I have is dl equals mu naught. Oh, and I have all that crap, don't I? I'm just going to leave it here for now because I'm going to deal with this. And what is the integral of dl? L. And what is L? The circumference. The integral of dl equals L equals 2 pi r. The circumference. Are you following me so far? So now we put all of this beautiful stuff together, and I get this. Boom, 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 and I get B 2 pi r equals r squared, big R squared, times I. And can we all solve for B? Yes. Oh, mu naught, sorry. Mu naught over there. Okay. So we get mu naught squared. Did I get it all? I think so. And how many of those are, okay, I'll wait till people get done writing. Is this starting to look more familiar? Is this about time that we can actually get this and we're not just gonna go, I can't do this, it's too hard? Okay? So, how many of these are constants? Everything but R. Therefore, B equals a constant times R. And the constant equals mu naught I over 2 pi R squared. And when something equals a constant times a variable, that is drawn how? That's a straight line, where the slope is that. That's the slope of the line. Yes? And once we get to the outside of the wire, what is little r now? What is little r now when we're at the outside of the wire? Big R. So I can just put a big R in there, and one of them cancels, which is our basic equation for the magnetic field due to a wire. And then if I go outside of the wire, then R on the bottom, because this at R equals R, B equals mu naught I over 2 pi big R. Yes or no? Outside of R, R is greater than R, B equals mu naught I over 2 pi little r. Because now it's a variable again. And as you get farther and farther and farther away from the wire, the magnetic field decreases as a 1 over r relationship. And I can graph this. So in this case, we have B and we have R, and it's going to be this until we get to R, and then it's going to go like this at a 1 over R relationship. Is it starting to look a little bit like something you've done? Ryan, is it looking more familiar?
Yeah.
It's still a lot of stuff.
Yeah, okay, so when you said at R equals big R,
See how I put a big R in there?
big R up there,
Yeah, because this is my magnetic field inside the wire, and it keeps increasing until I make this big R, and then one of the R's cancel. You see that?
yeah.
Outside of the wire, where do I get this equation from? That's just B due to a wire, which is on your equation sheet.
And did you get the graph again?
See how this is B times a constant times R, yes?
Yeah,
You see how there's only one thing that's a variable there, the R?
yeah.
Therefore, it really is just this, which is a linear equation with a y-intercept of 0. What's my slope? All that constant crap. And then, outside of the wire, it goes as a 1 over R. Now, how you got to conquer this, folks? You got to do it again with all the steps. When I tell you this is going to be a quiz that you have to do on your own, that does not mean you give me the answer. You have to give me all the steps. You have to say, here's Ampere's law. Here's my DL. Here's your draw it. Here's my I. Put it all together and get the information. Yes? Is this something I should be able to require of you now?
Yes.
Yes. All right. You have a weekend to do this? Next week we can make this a quiz that you should be able to take care of. Yes?
Yes.
All right. Can I go into capacitors, yes or no?
Yes.
All right. Go ahead and pause that for now.